So, really happy to be here, really humbled. This is my very, very first QCon, and I'm very happy to be here to present to you WebAssembly in the enterprise, secure, portable, and ready for business today. A couple of words about me. Probably you don't know myself. I'm Andrea Peruffo. I work as a principal engineer in Red Hat. And currently, my main focus is on Chicory and WebAssembly, which is the logo down there. And the one on the top is my little dog, Mido, that is looking at the sand and the sea into the city where I live, which is Lisbon. And it's actually a really great city to work the dog on the sand. And that's cool. Let's talk about what we are going through in this talk. We will have two parts. And the first one is about the motivation that bring this talk here at this venue and why and what we are trying to achieve. And the second part of it will be when the rubber hits the road. So use cases, practical use cases of WebAssembly, and all the troubles and the problem you will see and you will face and experience when trying to integrate your first WebAssembly programs into your applications, and how to overcome them to have actually great applications. A couple of words about WebAssembly. So first off, how many people have heard about WebAssembly before? Cool, everyone. So perfect. Just for the few of you that doesn't know about WebAssembly, is a portable binary execution format for programs. And it is extremely used in the browser. WebAssembly really loves the browser, to run in the browser. It has been built to overcome the limitations of running at speed, like graphic engines, cryptographic libraries, etc., inside the browser, where you can run only where you usually can run only JavaScript, which is a dynamic language, which is slow. Instead, now with WebAssembly, you can run system programming languages like C, C++, Rust, etc. And those are extremely fast. And they enable companies like Google to speed up their applications, like Google Maps, Excel, etc. And so even if you don't know, you are probably running WebAssembly behind the scenes in almost any site of a medium decent size in your browser. There are plus arguments to run WebAssembly inside the browser, which is the secure sandbox. WebAssembly is designed to be embedded into systems, and it will be executed in a secure sandbox that cannot be escaped, which means that the code that runs there will be completely controlled by the outside system. And this is standard. Is part of a W3C, so it is used today largely in the browser, and it is going to be used forever because it's a standard, and everyone can target it from the application development point of view and from the browser point of view. But we are in a track where we have to talk about server-side WebAssembly. And to talk about server-side WebAssembly, you have to see the power of this feature. What if we can take all the WebAssembly and all the work that has been done in the front end for the browser and bring it to our backend systems? In this way, we can have polyglot interfaces. We can compile actually from many languages to WebAssembly. So we can have plugin systems which are developed with on top of which can target WebAssembly, and is super easily embeddable. WebAssembly is designed to be embedded in a host programming language. So embedding it into another programming language feels like just natural, and you can follow the JavaScript APIs, but you can even go wilder and use different approaches, but this feels really natural and helps you design your system correctly. Is secure, as I told you. It runs in a sandbox. You have your memory completely, the memory that is used by the WebAssembly module is completely under control and is completely defined. So you don't have to think about strange things happening, but everything will stay within the boundaries that you have given. And again, it's a standard. So reusing something that has been built for a standard means that you can actually use those things for the years to come. So we are talking about many different things. So but when we talk about WebAssembly, we have always the two sides of it. We have many languages like Go, Rust, C, Kotlin, and Scala, and whatever, that can compile to WebAssembly bytecode. And then you have the other side, which is from WebAssembly bytecode, you want to run those WebAssembly payloads inside a system. And then you have a lot of different runners. Some of them, they come from the web browser, like the V8, of course, or SpiderMonkey, and these kind of engines. And some of them are new. And but executing a WebAssembly inside another language is a superpower. And that's why today we are going to concentrate and talk about running WebAssembly in Java, thanks to Chicory. Chicory is the project that I am the main maintainer of. It is a new Java WebAssembly runtime written in pure Java with 0 dependencies. So it comes and it can run basically on any JVM, stock JVM. So come send a star to our GitHub project, check out the documentation. Is actually pretty interesting, I guess. But why? Why? So I gave you a few motivations why we started this journey, but the full vision is the fact that, as it was highlighted in previous talks, the JVM is everywhere. We are running programs on Java in the whole infrastructure, in healthcare, cloud, wherever. So this is very, very widespread. And what can we do to unlock the potentiality of using WebAssembly inside those kind of services? And that's the reason why we started with Chicory. We have to think that there are many, many, many ways to integrate WebAssembly inside Java as of today, but most of them require foreign function interface. So you can call out to V8, you can call out to Wasm, but by doing a foreign function interface, so calling an external program to run your WebAssembly payload, you are effectively escaping the safety boundaries of the JVM. And this has a number of downsides. First of all, distribution. WebAssembly is intended to be a single target architecture that everyone can target and is completely portable across architectures. But if you have to ship a native library with your Java code, you have to compile it for the target architecture and operating system. So this is a problem because you always need to compile on the target that will run. Instead, with WebAssembly, this is completely decoupled, and you can just compile once to WebAssembly and ship your WebAssembly that will run unmodified on any different platform, which is ARM, PowerPC, or whatever, or even IBM Z in mainframes and those kind of things. And then you have runtime issues, because escaping the JVM doesn't only affect the capacity of the JVM to monitor and actually produce observability and monitoring on top of the application that you are running on it. So staying within the boundaries means that your program, your WebAssembly module will run within the memory of the JVM without escaping the maximum that you give, and this is extremely good for cloud-native environments, and it will have all the observability of that is provided by the JVM. That means all the debugging tools, etc., continue to work without any change. So we have the memory safety of WebAssembly. We have a fault isolation, because anytime that the native library, call it Wasm, V8, or any kind of native library that you will be running to run WebAssembly, in case the native library crash, it will crash your JVM. And this is, of course, something that you don't want to happen on your system in production, and is a benefit of running any kind of untrusted code, especially inside the JVM. And then you take advantage of all the other benefits that the JVM brings, that is also the just-in-time compilation, and your program will be completely self-contained because it runs with something that already knows. It's just on bare JVM. And yeah, that's why, at the end of the day, we decided that bringing WebAssembly payloads on the JVM is actually something really good, something that we want to do, and something that we want to enable. But we are just after lunch, and I see people sleeping, and I really want to wake you up and wake up your interest a little more. So during the next use cases, we will see a bunch of things, and our little slot will be our companion, our mascot in this. And now, when you see this, you should say slow. Be with me. 3, 2, 1. Yes. And when you see this one, instead, you have to see fast. 3, 2, 1. Fast. Yes. Thank you. Sorry, it's a little joke that my kids made up when showing to them those slides, and I have to bring it to the stage. Let's start with the first of the case studies that we have. The first one is something that I really care about because it's JRuby. It was the very, very, very first real-world use case we had for Chicory, and it's something that I really love. So we were developing this WebAssembly runtime, and we started, of course, with an interpreter. So just running the code in an interpreter inside the JVM. And JRuby people came to me and said, OK, we have something to talk about. But what is JRuby first? JRuby is an high-performance port of the Ruby programming language on the JVM. Why they did it is because you can take advantage, again, of all the benefit of the JVM, especially the threading model and the advanced just-in-time compilation of Ruby code. And it can run even faster than native Ruby code in some cases, especially for long-lived applications. So that's why JRuby is a super interesting project. But when you look at Ruby itself as a language, you have to know that Ruby is barely a user experience, or in most libraries and in most of the ecosystem, Ruby is kind of the DSL that you will use to interact with your system. Ruby has been done and developed to be really human-friendly, and this means that it tends to be really slow. So what happened is that below the surface, most of the code that you will be running when you are running, when you're developing Ruby applications, it will be C. That boils down to running directly on hardware, and that goes really fast. But there are very many problems into porting Ruby into different runtimes. The first one is that you have to do is the fact that when you want to port Ruby to a different runtime, you have to write a parser, and parsers are not easily portable. And the Ruby syntax has been done completely for humans, which means that it is extremely difficult to be interpreted and understood by computers. And you can find on the internet a ton of very different blog posts that are claiming how it's difficult to parse Ruby, etc. But this means that also that each port of Ruby for different platforms has re-implemented their own Ruby parser with different nuances, with different edge cases, etc. But we all know our industry, and we know what happened. So we have 14 standards, we need the 15th one. And I have to say that in this case, this is turning out and working out pretty well, as far as I'm concerned, and as far as I know, because basically what they did is we have a ton of different parsers for Ruby. Let's just build from scratch one with the current knowledge, after many years of trying to parse Ruby in many different ways, rewrite a full decent parser for Ruby, and it will be a C implementation, and it will be the unique one for all of the Ruby implementations. They have already reached 100% compatibility with all the parsers, which is great. So this project is called Prism, and I encourage you to check it out on the internet because it's really cool. As you can imagine, why we want to think about using Chicory in JRuby for Prism, because Prism is a C library, which can easily be compiled to WebAssembly. And if you run the WebAssembly inside a native WebAssembly runtime with zero dependency, you can boot it JRuby in any place where there is a JVM. You don't need to precompile your library, your parser, which is actually the very, very first brick of your infrastructure when you're trying to run Ruby code on a different platform. You don't have to recompile the parser for a different architecture. You don't have to recompile it for Windows. You don't have to recompile it for embedded operating systems or those kind of things. You just run what you have in WebAssembly. And this is really good and is extremely portable and enable JRuby to boot anywhere the JVM can go. So if you have even an embedded operating system where the JVM has been ported already, you can directly run JRuby and it will bootstrap in pure Java without the native dependencies. But imagine what? Let's see if you are prepared. 3, 2, 1. Yes. So running WebAssembly in an interpreter and running a full decent parser written in C on an interpreter is something really slow. And this was our first attempt and the first deliverable of the Chicory project, but we needed to go next. And to go next, what happened is that we implemented a WebAssembly to Java bytecode translator or compiler, or how we call it, AOT compiler, ahead of time compiler. If you think about WebAssembly bytecode and you look at it, it's very, 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 very similar to Java bytecode. It doesn't differ that much. And implementing a translator in between the two is extremely easy. And it makes it possible, actually, to run things much faster as they are pure Java code instead of having the need of an interpreter going through instruction by instruction through your code to be executed. At this point, using the Chicory ahead-of-time compiler, you can translate the WebAssembly payload to a class file, to a few class files and a few metadata that can be embedded without external dependencies into your final jar, and it will run as pure Java without any change, and it will take advantage of all the JVM things. And as you can see, performance are dramatically increased. We have from 10x to 30, 40x speed up by using the ahead-of-time compiler. And now we are, yes. At least you're awake, that's good. The second use case that I want to show you is from a friend of mine, which is one of the creators of TrinoDB, if you are familiar, or PrestoSQL, formerly known. Basically, what Trino is a distributed SQL database that happened to be written in Java. And at some point very early in the story of Chicory, one of the creators of this database came to us and said, OK, I really want to run Python on top for a user-defined function inside my database. And this was a big challenge, super interesting. The guy is David Phillips, and I really thank him for all the work that we did together to get there. Python and WebAssembly. Python actually really, really loves WebAssembly. Starting from the version from the release 3.13.0 of Python, WebAssembly is a tier 2 release target architecture, which means that is just behind the tier 1 architecture. So it is highly supported, it is extremely tested. This means that Python cares about being able to run on WebAssembly very much. In this case, I'm talking about not generic Python, but I'm talking about CPython, because how you run Python in WebAssembly is not by compiling function by function the Python code that you have, but is compiling the interpreter itself. So is compiling CPython to WebAssembly, and then you can run the interpreter of Python, CPython, inside any other WebAssembly runtime, which is actually interesting. But guess what? So when you start an interpreter and you have Python, and in this case you are constrained to a single thread, the first thing that an interpreter will do is to start to load the standard library of a language. The standard library of a language like Python with a lot of APIs, etc., is pretty big, and it has to load files from the file system and preload all the basic functionalities for you to be able to use. So imagine what this is going to be. Yeah. And to overcome this limitation, what happens is that you can start to take advantage of the amazing tools that are out there for WebAssembly. The first one is WasmVFS. WasmVFS enables you to have an embedded file system directly embedded into your WebAssembly payload, which means that you don't have to actually really access the operating system and load the file and then share the data with the WebAssembly module, but the WebAssembly module will contain directly the data that are on the file system and can directly read it. It has a few limitations. It is only for static file systems, and so the number of files that are there will not change during the WebAssembly execution, etc. But it's pretty good to at least encode the entire standard library and any kind of default library that you want to load into the environment by default. This is the first tool that we used. The second one is called the Wiser, and is a WebAssembly pre-initializer. What does pre-initializer means? Means that you can actually run your WebAssembly module up to a point, and at some point you stop the execution, you snapshot the current situation into another WebAssembly module, and the produced WebAssembly module will be extremely fast because it has already gone through all the initialization process and has done all the kind of operations that were needed to be run before actually starting, and you start from a pre-warmed up environment, and so you can actually be running something with a low latency and the pretty quick startup time that you usually have from WebAssembly code. And on the JVM, running in interpreter mode, so extremely slow, you can see that the initialization of Python used to take 40 seconds to load the entire standard library. After you use WasmVFS and Wiser, it takes only 1 second. We can apply, you can say that it's not optimal, but it's a big delta and makes something usable. And we can apply even further optimization to make it more appealing for a wider use. And with that, we have been, yes, again. I have a third use case, which is Debezium. Debezium is a super interesting framework that implements the change data capture CDC pattern, which means that is basically listening on your database or on your data source, which can be Postgres, MySQL, MongoDB, and a number of other static databases. And it will listen for changes, and it will propagate those changes as events to other different technologies, like Redis, but normally message queues and Kafka and those kind of things. So think of it of a glorified tail minus F on your database. Something is producing data into the database, you connect it to a different system, and you do it by propagating the events that are happening. And it happened that, if you think at it, Debezium is used as an architectural tool inside many Kubernetes native framework and infrastructures. So you know that Kubernetes is built on Go, but Debezium at its own core is really built up from on Kafka Connect, which is Java at the end of the day. So this is a Java framework that really needs to play well with the entire ecosystem, which is written in Go on top of Kubernetes. And one thing that Debezium lets you do on top of those changes is a single message transformation. So imagine that each event that has been produced on the database side will be emitted as an event, and it will be just one message that go through Kafka, and you can actually provide operations to be done on each of those changes. The most used one are, for example, filter and routing. So, for example, you can take one message, check if it has something in it, and decide if you want to move it forward or not. Or routing, delivering it to different things, different technologies, different queuing technologies on the downstream side. So how you make people write single message transformation in Go for Debezium, and this is the standard approach that you will take if you use a separate service or a separate container for doing this operation. Debezium is built on Kafka Connect, so it will receive a message from Kafka. It needs to deserialize it. It needs to serialize it back to go through the single message transformation that the user defined, that will deserialize the message again, reserialize it to get back into Debezium, et cetera, and this is, yes. And this is slow again, and this is not feasible and makes our architecture not usable by our user, and no one will really wants to use it for this kind of use case. That's why we implemented we have been running a single message transformation, especially written in Go, thanks to a Go PDK, plugin development kit, that will be used for writing those filters and routers. And those single message transformation will be able to lazily access the field of your messages. You can see that the PDK offers you helper methods to access through a pointer the object that has been deserialized into the Java heap. So you deserialize the message coming from Kafka Connect once into the heap memory, and then you give your WebAssembly module a way to lazily access each of the field by just navigating with a familiar dot syntax, its structure, and materializing only the value that they are interested in. If you look at this example, only the value.source.version will be materialized as a string inside the WebAssembly guest module, so that it can be compared with whatever, and you can decide to move on or not. But this is extremely interesting because you don't have anymore to reserialize the message which can be big, up to 1 meg or so, into the WebAssembly module, but you can access your host module. We said it before. WebAssembly has been designed to be embedded in other languages, and those are the kind of powers that you can take from it. And of course, this is yes, this is fast again, and we are happy again, we are going to be happy and run those things nicely on the JVM. Now, since I've heard about speaking about SQLite a lot during the previous talk on Swift, I want to speak a little bit about SQLite as well. SQLite is very popular, used everywhere, used on your mobile devices, on your laptops, and in a lot of desktop applications and any kind of system that you, or embedded devices, everything that you can think about. So it's very, very widespread. But we don't have a really great SQLite story into the Java world, so SQLite is not really used in many Java projects because SQLite is written in C. And having to call from Java to C, you incur in all the kind of problems and issues that we have analyzed before. But we can reuse the ahead-of-time compiler we spoke about that we used with Prism and JRuby. So we take a SQLite amalgamation, so the exact source code that is produced by SQLite and is distributed as releases of SQLite. We compile it to WebAssembly first. And once we have the WebAssembly version of SQLite, we translate the WebAssembly bytecode into Java bytecode. So this runs exactly Java methods on top of the JVM. So we have all the functionality of SQLite directly embedded in a Java program. But imagine what this is. Yes, running all those C functions and all the algorithms that are running in a database, etc., translated from Wasm has problems. And we noticed it to be really slow, and we started profiling to understand what was the root cause of the problem. Now you don't see this flame graph very closely, but what has been highlighted there that takes most of the span of this flame graph, so which is at the end of the day going to take most of the time of your execution, is the call to the memory grow methods of WebAssembly. How memory grow works is memory grow means that SQLite wants to allocate some space to allocate a string or allocate some space in the heap, and it asks to grow the memory a little bit because it doesn't fit the current size of the memory. And SQLite happened to call the memory grow methods one by one for each memory allocation that exceed the current size of the memory, which means that now you have a memory of 1, but you need to store 2 bytes, and they call memory.grow with 2 to be able to store whatever is needed in SQLite for 2 bytes, and then this happens again for 3, for 5, etc. But those little incremental grow are done subsequently and for each and every allocation that has been done into SQLite. And this doesn't look that bad, but our first implementation of the allocator was just respecting what the guest module, so SQLite in this case, was asking. So it was growing the memory according to what the WebAssembly module asked for. This doesn't, but growing the memory is extremely costly because the WebAssembly memory is defined, and in this case, especially in this case, it's just a byte array. So you have to think about the guest module memory as just a byte array. But for growing it, you cannot simply resize the array. You have to create a new array with a new size, copy all the content of the previous array into the new one, and go on from there. This is an extremely costly operation. And if you start doing it over and over again, you end up with a graph that we have seen. So we implemented pre-allocation, which is nothing new, but what happened is that basically when the WebAssembly module asks us to 2 bytes of memory, we just pre-allocate a whole chunk and show to the WebAssembly module the 2 bytes that he asked for. So we decoupled the memory that is being allocated by the runtime from the memory that has been requested that will be requested from the WebAssembly module. In this way, most of the operation of memory grow will be a no-op at the end of the day. And you can see that this was macroscopic, even running a test. And in this specific test, we have been running like 50,000 or something insert. And it was extremely slow. It was taking more than 50 seconds to execute a single test. And with just decoupling the memory that is allocated by the runtime from the memory that is requested by the WebAssembly module, we have been able to be again, yes. So I want to, we have exhausted our use cases, and I want to see some conclusions about using WebAssembly in real world project nowadays. When you need safety, so to be in very secure environment, when you want to port your plugins everywhere you want, when you want to be fast, because at the end of the day, WebAssembly has been designed to overcome the limitation of JavaScript of not being fast enough, and when you want to be polyglot and get your users to write their functions in any language they want. And especially when you have a constrained problem, this, WebAssembly works extremely well when you have a very, very stable C, C++, Rust, so low-level API, which is really well-defined, or when you have an application binary interface, which is very stable, like for a single message transformation or for queuing systems. So you have a very, very clear demarcation, very clear boundary in between your application and what the WebAssembly module should do. And there are a lot more use cases where you can use it. Well, in this case, you don't have to fear the slot. Your program doesn't need to be slow and doesn't need to run slow, and you can actually take advantage of WebAssembly and run it fast again and actually execute on any platform that you care about. With this, thank you very much to everyone, and I'm happy to take a few questions. Yeah, so we are working. I'm currently working full-time on Chicory, so on its implementation, on the core implementation, and we are actually implementing a lot of proposals now. So we have exception handling already implemented for the interpreter that we are moving to the compiler now. And the next one will be WasmGC, which will be an heavy lifting to be able to run Kotlin, Scala, Dart, for example, on top of Chicory. So this is regarding the core development that we are doing, and regarding use cases as well. We are looking at having much closer integrations with other runtimes, with some projects, to be able to make this technology and making WebAssembly actually run on top of in Java user applications without even people noticing. And the first one that I will be probably focusing on next will be a tight integration with a quick.js runtime, which enables you to run JavaScript in a sandbox environment. And this is extremely useful for Java programs that are compiled nowadays more often than not with a native image of JVM, so they are very, very static, actually, programs to restore the dynamicity that we used to have on the JVM to be able to run JavaScript, in this case, for plugins and those kind of systems. But I'm happy to hear even more use cases and to support them, because we have many things going on.
done with the response. Thank you for the talk, first of all. And second of all, there is another tool that Red Hat says that it's super fast, and that's Quarkus. How do you see WebAssembly and Quarkus, or Chicory and Quarkus joining forces?
Well, Chicory has been designed ground up for running in Quarkus. It runs in Quarkus. It just generates pure bytecode, which is what Quarkus really loves. So you can just run Chicory. You can just use Chicory, produce the bytecode that you need, and if you go through a Quarkus application, it will be you take all the advantages of compiling with native image or running at the speed of Quarkus. For the future, we are foreseeing much closer integrations with the framework to be able to take advantage of Chicory much more easily with a more Quarkus idiomatic API, other than being just two separate projects that happen to play well together. So, no one? Oh.
How does the sandboxing in Chicory work?
So the sandboxing works as any WebAssembly runtime. So the first thing is the fact that WebAssembly defines that your memory is bounded. So it has an initial size and it has a limit. How it is implemented at the end of the day is nothing magic. It's just a byte array, literally. So the memory safety or your WebAssembly module are dependent on the size that you define your byte array, that is the memory for the module. And this is extremely safe. So you don't have out of memory, you don't have nothing. This is allocated by the JVM, is fully inside the JVM. The second question that normally comes with this one is the fact that you need usually to bound the computation as well. So you need to bound the CPU time that your WebAssembly module will be using. And this thing is tackled in two different ways. The first one is honoring the thread interruption on the JVM. So this means that if you run your WebAssembly module on a thread and it will receive an interrupt, this will be honored as satisfied. So the program can easily have a timeout. So you can easily time out after 10 seconds, whatever, the execution on top of the CPU. The second way is a very, very low-level listener into the interpreter, and this is not available when you translate from WebAssembly to Java bytecode. But in the interpreter, you have a very low-level callback at each execution, at each opcode execution. This means that you have very, very, very low-level access to what has been executed in the WebAssembly runtime. And you can implement things like fuel or run for 1,000 instruction or run for 1,000 instruction that only contains certain things, etc. This is what we have. I hope I have covered your question.
Hi, I have a follow-up on this. So if you use ahead of time compiling, you inject instructions that from time to time check the thread interruption?
No, I said this before. This is available only in the interpreter mode.
So in AOT, you can't actually interrupt the thread?
Oh, no, thread interruption are not injected, but they are encoded, especially in all the control flow instructions, all the sensitive control flow instructions. So we are not checking for interruption during normal code execution, but we only check for interruption during control flow. And control flow happens pretty much very often in any WASM module for doing anything useful. So we do check for interruption in loops, blocks, unconditioned jumps, and those kind of for those kind of opcodes. And this is happening as well in the translated Java bytecode.
And this generates a trap, or you can continue?
It generates an exception.
Okay.
Are we good? Yes, I just want to remember to save the date because I'm just back from Wasm.io and it's an amazing conference. So be sure you watch it out for next year. And thank you so much for being here today.